Good morning, team. Chemistry coach coming at you again. Are you sick of me yet? Hopefully not, right? We're learning some chemistry here today. All right. So we looked at closest packing in the last video, specifically for metallic solids, right? Take the marbles, dump them in a box. And we specifically focused on cubic unit cells. So we had to get the FCC, BCC, simple cubic, and we did a poke into hexagonal closest packed as well. Well, I want to complicate it a little bit. What if we have something where not all of the particles are the same, right? For metals, all the atoms are the same. Well, let's take a look at ions, right? Ionic solids, where you have cations and anions. Right? Obviously, the cations are going to be repulsed by other cations, but attracted to anions. Anions are repulsed by other anions, attracted to cations. Like charges repel, opposite charges attract. So would it make sense when these pack, they're going to do it in such a way to maximize all of those electrostatic attractions and minimize all the electrostatic repulsions? Oh, I would agree with that. So there's some estimates we're going to do. It could get this. We could open a big, ugly door here if we wanted to. There's some pretty crazy ones. I'm going to just introduce you to the concept of how we think about it and just focus on simple ionic compounds, your typical sodium chlorides and whatnot. All right. So when we're packing ions, I'm just going to focus on cubic unit cells. All right. I'm not going to do the other ones. All right. So this is the way we think of the packing of ions, most estimated. Okay. We're going to take the larger, typically the anions are larger, typically. So that's going to be the case we're going to be thinking about. Those larger anions are going to pack just like we thought of with the metals. So if you just ignore the cations, think of the anions as like metallic atoms, they can go into the spaces for the FCC, face-centered cubic, where you got them in the corners and on the faces, or maybe simple cubic, just the corners. We could even do body-centered cubic, but that's not, I don't think I've even seen an example of that yet. So most commonly it's going to be FCC or simple cubic. FCC by far the most common. Right? And if you're in doubt on my exam, right, go FCC, but I'm going to show you a way to kind of calculate that real quick towards the end. So now that we've got the anions placed, they don't like each other, right? So the smaller cations, remember there's holes, right? There's holes in there. There's spaces. There's voids in between those particles. So the smaller cations are going to fit in those little voids or holes in between the anions. Oh, snuggle in there, push those anions a little further away from each other. Yay, minimize the repulsions, and then snuggle in, and those cations are going to nestle up to the anions, maximize the attractions. See how that makes sense there? So let's take a look at some FCC and simple cubic arrays of anions and the different types of holes that can appear for cations to jump into. And it really depends on the size of the cation relative to the size of the anion, right? What if you have really big anions and really little tiny cations, or medium-sized anions and cations that are approaching the size of those? Really makes a difference. So let's look at the different types of hole options we can run into in the next board. Good luck drawing this. This took a while. All right. Don't have models of this, unfortunately, but here's the four most common ones that I've seen. All right. And these are all cubic unit cells. Okay. So these first three have an FCC anion packing, where you have the corners and the six faces. 8 corners, 6 faces, 8 corners, 6 faces, 8 corners, 6 faces. That gives us 3 different kinds of holes. And the last one is a simple cubic packing of the anions, where they're just in the corner. So I'm doing the anions in brown, and I'm trying to outline in red where the hole is, where the cation would go. Right? So let's take the first one, called the Trigonal Hole. So I filled in the anions that are not part of that hole, and then what I did is I did kind of that the dashed one. So you see this one right here on the front face, this one on the top face, and this in the upper right corner. Those 3 form what's called a trigonal hole. Little tiny hole, that's the smallest one. So really small cations like to go in trigonal holes. If we look at the tetrahedral hole, right, you've got the FCC array, but you've got the anion on this front face, the right face, the top face, and the upper right-hand corner. So it's a little bit bigger. So those 4 anions form what's called a tetrahedral hole. And if the cation goes in there, a little bit more space, so slightly bigger cations like to go there. right? The cations like to go in there and push those anions apart a little bit. We're going to do some calculations to show you how to predict which hole it goes into based on the anion and cation. So you're going to need, from one of your earlier chapters, most likely find a table of ion, cation, and anion radii, or sizes, typically given in a radius. So you'll need those numbers to be able to do the calculations in a little bit. All right, let's get to a slightly bigger hole here, octahedral hole. So let's take that FCC array, look at all 6 faces, front, back, left, right, top, bottom. Those form a little octahedral-like cage where the cation would go right in the middle there, okay? Bigger space. That's probably the most common one I've seen based on the ratios of cation and anion sizes that I've calculated. The majority fall into an octahedral hole. Yay! And one that is not as common, you got to get really big, where the cation is approaching the size of the anion. It's going to need a lot of space. It's not going to, a little too squishy for these ones. So here you get a simple cubic array where you just have the anions in the corners. And then kind of like in a body-centered one, but the body atom would actually be this really big cation with these roughly similar size anions around that size. So smallest holes here, all the way across to the biggest. So trigonal, tetrahedral, octahedral cubic holes from smallest to biggest. And so smaller cations prefer these, middle-sized cations prefer these, and large cations prefer these. Let me show you how to predict those. Actually, I'm going to unpause for a second if you are feeling daring and want to attempt to draw those, right? But probably you could find these in a textbook anywhere. I hate to say go Google it. You never know what kind of garbage you're going to get for to run on the internet, okay? So try to find at least a credible source, ideally your textbook if you have one. So if you want to take a chance, do my best Vanna White. Hey, pause it. Give it a shot to draw. And again, the ones with the dashes in brown, those are the anions involved in forming the hole. Okay? Freeze frame. Now you got it. Let's take a look at the octahedral hole as an example, but you could do this for the trigonal hole, tetrahedral hole, simple cubic hole, whatever you want. But we're going to try to figure out the ratio. The key, right, is the cation has to fit in which hole, right? And it has to fit in a hole so that the cation is a little bit bigger than the closest packing one, right? So you put the cation in there, I should just be touching the anions. We want it a little bit bigger to shove those anions a little farther apart to minimize those anion repulsions and make sure that cation and the anion are smashing up against each other, right? So that cation needs to be just a little bit larger than necessary. We're going to create an equation to predict for this based on the cation ratio, the radius of the cation to the radius of the anion. Just calculate the ratio, shows you which hole to put it in. So let's show you how we get that ratio, just for this one, and then I'll just list them up for all the other ones. Let's take the octahedral hole again. These take forever to draw. It broke my heart to erase the last board. So we've got the 8 corner atoms here, or anions in this case. And then we've got the 6 faces, and then the octahedral hole is in the middle of those 6 facial chlorides, right? So it's a pretty big hole. Let's take the facial anion on the left, right, back, and front, and flip it. Let's look from the top down. Let's take this. So these brown circles would represent these facial anions. And then you've got the cation in the center of that octahedral hole. So they would be touching like this. And what we're going to do is calculate exactly what it would take to fit in there. And then the radius of the cation we need should be a little bigger than the answer we're going to get. So I'll do it with an equal sign, but then at the end we'll put a greater than sign, okay? Well, do you see that little triangle that forms? Oh, does this bring back bad memories? The Pythagorean theorem? Oh, yay. So we've got a right triangle here between this base here, this side here, and then the hypotenuse going across, right? So let's go ahead and do the calculation. We know that a squared plus b squared equals c squared. That's from the Pythagorean theorem, right? You gotta love this geometry. I hope you paid attention in high school, my friends. Well, let's take a look. Well, this would be A, this side here. This side would be B, and then the hypotenuse, the diagonal going across would be C. Well, in terms of radius, what would A be? Well, would you agree that this is the radius of that anion, and that's the radius of that anion? So that would be 2R. So A equals 2R. So capital R will be the anion radius. That would also be true for B, correct? We got the radius of an anion there, radius of an anion there. So we get 2 times capital R for B. If we square that, you get 2 times the radius of the anion squared plus 2 times the radius of the anion squared. Now let's look at C. Do you see that that's the radius of the anion here, the radius of the anion there, and then we have the entire diameter of the cation, which would be R and R. So let's use little r as the cation radius. So that would be little r and little r. You probably can't even see that, right? But would you agree that that would be 2r? So this would be 2 times the anion radius, there and there, plus 2 times the cation radius, or just the diameter. 2 little r squared. There you go. So we've just identified A, B, and C from this. My door is creaking open, so I'm going to go close that. Either a child is sneaking in or a cat is sneaking in, one of the two. So what I want you to do is go through, use your best mathematical skills in algebra, and I want you to solve for little r over capital R. I want you to get that ratio and see what number you get. I'm going to go close the door real quick. Yes, it was a cat. With 2 cats, actually. I just want to stand in front of the computer. All right. So, got some fun algebra over here. I skipped a whole bunch of steps, but we'll talk through it. All right. So, let's take 2r squared, right? So, 2 squared is 4 plus r squared, and then 2 squared is 4. So, 4 plus 4 would be 8, correct? So, this would be 8 times the capital R radius of the anion squared, equals the right-hand side, which was c squared, right? 2 times the radius of the anion plus 2 times the radius of the cation, square the whole enchilada. We're trying to isolate the ratio of the cation to the anion and see what that should be, like minimum. All right, well, these are all squares, so let's take the square root of both sides, right? Square root of this would be the square root of 8. Square root of r squared is r, so that'd be the square root of 8 times r. Square root of that just gets rid of the squared term, so that would be just 2 capital R plus 2 little r. And now we want to isolate. Let's get the capital R terms both on one side. So let's subtract 2r from both sides. So we're going to get square root of 8 minus 2 times the anion radius. So I just factored it because it'd be square root of 8r minus 2r. So you just factor the r out, right? That would equal 2 little r, right? Radius of the cation. And then just divide both sides by 2. So I'm going to get the square root of 8 minus 2 times capital R divided by 2 equals little r, the cation radius. And now just divide both sides by capital R. So little r, the radius of the cation, divided by capital R, the radius of the anion, would equal 0.414. If you take the square root of 8 minus 2 divided by 2, that'd be 0.414. And remember, that would be perfect closest packing. So it needs to be a little bit bigger than that to fit into an octahedral hole properly. So the radius of the cation over the radius of the anion needs to be a little bit bigger than 0.414 for it to fit into an octahedral hole, right? And that'll extend for a range until it gets too big, and then it would go into a cubic hole. So I'm not going to make you suffer for this for the trigonal, tetrahedral, and cubic holes. Not going to do it. So what I'll do on the next board is just summarize the ratio of the cation radius to anion radius and what ranges they need to be to fit in trigonal, tetrahedral, octahedral, or cubic holes. Whew! How many times do we got to do Pythagorean theorem? I love it, though. Once you walk through it, it's not too bad. You ready to predict? All right, so we only calculated this one number, the 0.414. That was the minimum size necessary for an octahedral hole, so the ratio of the cation to the anion would have to be a little bit greater than 0.414 to fall into that octahedral category. But if we did that for trigonal, right, that would be 0.155 if we did the same calculation we did for the octahedral. For tetrahedral, it would be 0.225. That ratio is just the minimum amount. And for a cubic hole, it's 0.732. So it'd have to be a little bit bigger than 0.732 for that ratio to fit into that and push those anions apart a little bit. Which means if that ratio of the cation, little r, to the anion, big R, is bigger than 0.155, but less than 0.225, that would mean that that cation would have to fall into a trigonal hole. That'd be a really small cation, right? Larger anion, smaller cations. So that's the smallest hole type. Okay? Pretty rare, but possible. So if that ratio of the cation to the anion radius, and you need those values, so find a table of those. If it's bigger than 0.225, the minimum required for a tetrahedral hole, but less than 0.414, the minimum required for an octahedral hole, that ratio would give you a tetrahedral hole, a little bit bigger, right? So that cation's a little bit bigger, or at least the ratio. It really depends on the ratio. But assuming the anion was the same, then you've got an increasing cation radius, right? Now, if it's a little bit bigger than 0.414, but less than 0.732, that ratio, it falls into an octahedral hole. A little bit bigger, most common one that I've seen. And if that ratio, if that cation is really big and that ratio is bigger than 0.732, heck with the FCC. It's going to go to a simple cubic lattice and fit into a cubic hole. It's just the cation's too big, right? Smaller to larger. Let's do a couple examples and show you how simple. Once you have this down, easy peasy. I'll do one, and then I want you to work on the other one. It's real. If you know how to do these on an exam, woo, piece of cake. I will always provide you the radius for the cations and anions. You don't have to memorize those. Or I could give you a chart of them, so you can just read out the chart. Usually you'll find one in an earlier chapter from last semester where it has all the atom sizes and the trends getting bigger going down and smaller going left to right. And then usually right below it, it has the cation radius, which is a lot smaller than the atom, or the anion radius, which is bigger, right, than the anion. I mean, than the atom. So let's take lithium chloride, right? Of course, that would be the lithium plus 1 cation. And if you look up on the table, that has a radius of 59 picometers. And the chloride minus 1, right, which has a radius of 181. So the anion's way bigger. That chloride anion's way bigger than lithium. Tiny, tiny. It's way up on top of the periodic table, right? That's my periodic table. So lithium's way up here, so that's going to be pretty small. And of course, as you're going across, it gets bigger. And, it gets smaller. It gets a little smaller, but then you go down to a whole new shell. So chlorine's way down than lithium. So it's in a bigger end level. So it's going to be a bit bigger. Quite a bit bigger. So let's take the cation radius over the anion radius. So 59 picometers divided by 181. Those aren't exact numbers, by the way. So that'll leave me with 2 sig figs, giving me a ratio of 0.3259. Good to 2 sig figs. Sig figs aren't too critical for this. Well, that falls into the tetrahedral hole. If you look at those ratios that we talked about. So tetrahedral, what did that fall between? I forget what that was. Tetrahedral, I think, fell between 0.225 and 0.414 or something like that. So that falls in there. It's bigger than 0.225, but smaller than 0.414. So it's too small to go into an octahedral, but too big for a trigonal. Okay. So do the exact same thing for potassium bromide. I want you to find the radius of the potassium ion forming. And then find the radius of the bromide forming. So go look those up in your textbook or something like that. Write those down, calculate the ratio. Tell me what hole that's going to be in. I'll give you a few minutes and then I'll pop that up on the board here. Did you get what I got? So I looked up the potassium ion, found that 138 picometers. Looked up the bromide ion, 196 picometers. So they're getting closer. So that's a bigger cat. Potassium's obviously bigger than lithium. Right, so lithium's here, potassium's here. That's 2 n levels down, so potassium's going to be a lot bigger. Okay. So if you take the cation ratio to anion ratio, the radii, take 138 picometers of the cation divided by 196 picometers of the anion. Go to 3 sig figs, so I get 0.70408. 3 sig figs there. So that falls in between. So it's a little bit bigger than the 0.414, is it, necessary for an octahedral hole? But it's not big enough. What's that, 0.732, I think it is? It has to be bigger than 0.732 to go in a cubic hole. So that falls in that ratio necessary for an octahedral hole, would fit in real nice. If that had been greater than 0.732, we would have had to say a cubic hole because it would have been too big. So not too bad, right? Not too bad at all. So let's take a look and see the other thing about ions, cations and anions. The way they're packed in there, the way the cations and anions are packed in there, you have to end up with the proper ion ratio, right? See the 1-to-1 ratio of cations to anions here, 1-to-1 here, right? Or magnesium oxide, or if you had, magnesium bromide, MgBr2, you'd have to look and see inside that unit cell how many cations there are, how many anions there are, and look at the ratio, and that should match the formula unit for that particular ionic compound. I'll just do one of them for you. Let's do like potassium bromide, and then show you how we end up with a 1-to-1 ratio, and we'll be done with ionic solids. This is tough to see, right? And this is one of the easiest ones to do. But if we're trying to show that the packing of cations and anions matches the formula unit of that particular ionic compound, this spatially can be tough to look at two-dimensional pictures, right? So I have this. I don't know if this will help. So again, the ratio of cations and anions, so just like we counted them before in FCC, BCC, simple cubic, right? FCC was 4 atoms for metals, BCC 2, simple cubic 1, et cetera, et cetera. But now if we have ionic compounds, we have both cations and ions. So you have to count how many anions are in there based on the FCC, simple cubic array, whatever. Those are easy. The cations are a little tougher because they're in the holes, so it's hard to see. For example, potassium bromide. Let's do the brown ones as the bromide ion, so you can see they're in the corners and the faces. Everybody agree? We got the FCC, face-centered cubic array of bromide ions. Potassium ions go in the octahedral hole because of the ratio of the cation radius to the anion radius that we calculated on the last board. Would it make sense to you, since the bromide anions are in FCC array, you've got 8 in the corners that are 1/8 each, so 8 times 1/8 is 1. You've got the 6 faces that count as a half each, right? They're shared. So 6 times 1/2 is 3. So 3 plus 1 is 4. There'd be 4 bromide anions in that FCC array. But then we've got the cations in the octahedral holes, right? A little harder to see. So let's take a look at this. I don't know if you can see this. Imagine the red ones as the bromide. So you see the corners here, right? So you got the corners. Ooh, that's tough to see. I got too many here. So corner, I'm going reverse what you guys are. Corner, face, right? And then you've got the face, corner. So this little chunk right here is 1 unit cell. And you can see that gray one right there. That'd be the potassium in the octahedral hole. But when you extend out multiple unit cells, you see how you now get them in between. So here's the corner and corner up on the top. You get one in between, corner, one. So you get them on the edges, right? So they're on the edges there. So you've got 1 potassium ion right smack in the center of the unit cell, and then you've got 1 on each edge. So you get that alternating 1-to-1 ratio. Well, I drew in green all the potassium cations on the edges, which are shared by 4 unit cells, right? If you're on the edge like this, living on the edge, wow. I won't try to sing for you. I used to actually be I got through college on a scholarship singing as a tenor. But then I coached softball for like 13 seasons, and I've been coaching baseball for 6, I think, and still going. All that, hey, especially these, like 8 or 9-year-olds are playing in the dirt, hey, turn around and face the ball. You're going to get hit in the head, and you're yelling across the field. After so many years of doing that, my voice just got shredded. So much for my tenor career, right? I'll stick as a teacher bellowing at you guys, right? And normally I teach, about 140 typical size for my classes. So I got a large lecture hall and I'm bellowing. I don't like microphones. Just feel like it's, a walk and it hooks on it. So heck with the microphones. But anyway, if you've got an edge one like this, right? So you've got this one, you have another one on top, one on bottom. So that's shared by 4 unit cells. So each edge, so if I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges times 1/4 each, that would be 12 times, that'd be 3 total atoms. Plus you've got, I did in red, the center one in the octahedral hole, in the center of that unit cell counts as 1. So 3 plus 1 would be 4. So there's 4 potassium cations in there. Well, that'd be a 4-to-4 ratio. If we reduce that, that's a 1-to-1 ratio of potassium ions to bromide ions in this unit cell. This is the simplest one. So you can look at your textbook, and there's some tougher ones, but it matches. But there's a few where even I'm looking at it on a 2-dimensional. I'm like, not going to happen. I need a model to be able to see, because sometimes you can't tell. Is that cation inside the unit cell, or is it partially? It can be very challenging. All right. So I just wanted to give you an idea how that's done. Boom. Let's move on to a couple more, 2 more videos. We're going to be looking at X-ray diffraction, how we can use that to determine the edge length and the radius right? For those kinds of things, we already have formulas that relate the edge length to the radius, and if we just cube the edge length for a cubic unit cell, we can get the volume. And ultimately, we want to use that to calculate the density. If you know how many atoms are in there for metallic, you could do it for ionic ones too, but we're only going to do it for simple metallic ones. So if you know how many atoms are in there, you can calculate the mass in grams. And if you know the volume, you get that in centimeters cubed, you can calculate the density in grams per centimeter cubed. Boom, let's do it.